Hello again, welcome back to Information Storage and Retrieval. So, today we're going to talk about normalization and phrases. Now, we've heard normalization before, and we've already talked about phrases. We're going to dig into a couple of different ways to work with both of these processes. Just to recap, as always, this is going to get a little stale for you at some point because we're doing the same recap over and over. But it's key. I want to make it clear. We've covered indexing, and indexing is the big thing, right? The big thing that we do, the big tool that we use to make sense of our documents and turn them into a searchable system, right? And that process is inverting the documents from all the terms in the documents in their document order, which is, the sentences, the paragraphs. The words in a document show up in the order in which they were written into the document, right? We flip that on its head to put the documents in term order. So the postings for each document are listed for each term. This is the beating heart of all these systems that we are talking about. This is the primary process. It's efficient. We've talked about how it can be stored in across multiple disks. It's portable, it's flexible, and it's efficient. So this is a good way to make user search possible. And it's also consistent. We are doing the same process most of the time in the same way. So it's mostly the same thing that we're doing at the core of a search system. But there's also a lot of variations to be made, a lot of questions to answer about your search system, right? Anyone building a search system from scratch has to make a bunch of decisions about how to approach their particular search problem. We already discussed last time about how to select, or the trade-offs of selecting document granularities, right? So too small, too large, all those issues. And also some additional ways to index things that help you achieve different variations on search, right? So if you want more general searchable ability by exact lexical order of characters, you can use kgrams as tokens. Or if you want something a little bit more specialized, you could build phrase indexes where phrases are the tokens, or proper nouns where proper nouns are the tokens, that kind of thing. So today we're going to talk about some more variation, ways to further normalize text. We talked about some basic stuff, but there's other ideas we can dig out for normalizing text. And then we're also going to talk about a new kind of index, actually. So, like I said, variations. It's still the same basic process, but we're going to store a little more information in this index so that we can do both terms and phrases. Aha. Très interessant. So, normalization. We are taking... The idea of normalization is taking very similar words out of our text, very similar tokens, and we're trying to get them to be considered the same term, right? So sometimes that's just about the letters, the capitalization, the punctuation, right? We're saying don't, and don't, whatever, are all the same idea, right? But other times we might have to dig a little bit more into the semantics and say, okay, well, these two words, they're kind of the same thing, and especially like different forms of a verb, for example. Run versus ran, right? Those are both fine in terms of the concept, right? We know that run and ran are the same basic idea, but they would not turn up. There's no way to just like force lowercase and make the two different phrasings of that work together. So, moving with that example, we're going to talk about a few different things in the normalization process. So, equivalence classes. This is a bigger, broader theoretical idea. About asymmetrical equivalence, we'll talk a little bit about accents and diacritics, and we'll dig into case folding, and then the bigger, kind of most interesting process is stemming and lemmatization. So let's talk about equivalence classes. This is the big concept for how we get all of the different raw text tokens and say, these are all the same. These are all together. An equivalence class is any set of tokens that we want to treat as identical. So don't, all those. We want to have the different capitalizations, the different punctuations. We would say these tokens all fit in the same equivalence class. So anytime you do token processing, anytime you do text processing, like forcing lowercase or removing punctuation, we are creating equivalence classes, don't and don't, right? But sometimes you might want to define them on your own with your own set of equivalence classes, because you know that if someone searches for car, they might also want documents that have the word automobile, right? That just makes sense, but there's no way that your system is going to automatically collapse automobile to car, right? So you would have to, if you want that equivalence class to exist, you have to create it. You have to manually program a step in to say, now convert all car texts to automobile text. You'd probably go the other direction because automobile is longer, right? So let's look at this. Here's an example. If I do the query window, right? I would want window to pull up a few different things, like an actual window, right? I would love for my search for window to come up with window, right? That seems very basic. I might want it to come up with the plural of window, so windows, right? If I'm shopping for windows, I would want these things to work. Now, if I type windows, well, that's good. It maps to the plural, but I'm probably also searching for something else that you might know. Perhaps an operating system, right? Whereas if I'm looking at capital Windows, that's probably me being very explicit in my search. We wouldn't necessarily want to collapse that to the same term as lowercase windows, and certainly not to just window. Because no one's ever going to search. They know that the name of the operating system is Windows. And if they're capitalizing it, that might be important. So, these are what's known as asymmetrical equivalence classes. It requires a lot of effort. You have to parse queries and like disambiguate them at the step of figuring out where am I actually pointing to in my terms, right? So, you have to either do this when you're building the index in the first place, so making lots of different terms from a single term, or while you're processing the queries. So it takes effort to do this, but again, we're always talking about things, about the tricks that the big shots do to make sure that you get to your desired search results. And this also gives us the ability to differentiate, right? So it costs something, but it gives us this new ability in our search system. So window might map to both window and windows. So again, this could be when I'm processing the text into the index, or it could be when I'm processing the query, saying, oh, wait, I know that this query expands into two other possible queries. I'm going to turn up everything. So instead of the intersection, right, I could say, here comes window. I'm going to look for all the tokens that have window or windows, because I'm cool with that, right? Versus capital Windows, maybe we should just keep that one as it is. Maybe that should be caught by a very specific proper noun type index. So that's the idea. Equivalence classes are they're just a property of what we do here. When we are collapsing terms from the raw text into a different kind of text, into tokens, into the terms of the tokens, then that is creating an equivalence class. And sometimes we want not one-to-one mappings. We want some interesting little tangled things, like in this example. Let's also talk about accents and diacritics. Okay, so these are the little decorations that appear on your on your text, right? So sometimes it's superficial. The word cliché versus the word cliché, the little accent, that's not a big deal. That doesn't really change the meaning. People know what cliché means, right? Cliché, right? But sometimes it matters quite a lot. Peña in Spanish is cliff versus pena is sorrow. Although I may have gotten that reversed. So if you speak Spanish, correct me. But so the idea being that the ñ, the little tilde above the n, not only changes like how the word is spoken, but it completely changes the meaning of the word. Yikes, that's not great. That's important for our system to be able to capture. But here's the problem. People typically skip typing these things. So the standard solution is just to ignore them and collapse them as normal. But again, we're talking about variations. Perhaps your system needs to take this into account. Maybe you're working explicitly with like song lyrics in multiple languages. You would need to keep track of the ñes and the umlauts and all that important stuff. So again, these are decisions that you can make at the time of building your indexes and the way that you decide to process your queries. And again, we are inserting one small step among all the rest of the steps. You could say, hey, wait, I'm gonna keep the accents and diacritics. I'm not gonna fold them into the same text. I'm gonna hang on to these. That is a decision you make about how your system works. Another element is case folding. So this is what we've already talked about to an extent, and what we will do this in the assignments. Capital letters, right? Those are everywhere. They're all over our language, at least English, but a lot of languages have that same convention. So we can just force everything to lowercase, like we've talked about, but we're losing a few things when we do that. So we can selectively case fold. For example, the idea being that if someone chooses to capitalize words in the middle of a sentence, that might be very important to the meaning of that word, like with Windows, right? So a sort of a nice rule of thumb that these systems typically use is maybe just convert just the first word of the sentence to lowercase. Let everything else stay capitalized in the way that it's used in the natural language. That's fine, but it's also, as with all of these different variations, we have to consider what the user is going to do, because a lot of users are just not going to type the capital letters, right? So most Google searches are all lowercase. So again, including very specific solutions for case folding, for forcing lowercase, for example, it adds to your precision. It makes it so that my search for Windows is going to find Windows, right? But we always need to consider the use case, right? So the user who's rapidly smashing things into their phone is not always going to capitalize things in the same way. But that's the idea. So these are all different ways that we have talked about how do we create useful equivalence classes in normalization, right? Another one that's quite useful is stemming and lemmatization. These are both, they get to the same idea, but they achieve it in different ways. So many words have the same, like almost the same meaning, and they share the same features. So the stem of a word is anything that has the same characters at the beginning when the words are all the same meaning. So, operate, operates, operation, operational. What do those have in common? They have operat, because they're all using a slightly different suffix, right? But they're all in the same zone. I need to, of course, I would mean to find operational if I type the word operate. To create a useful equivalence class for that, we can stem all of the words in the documents when they're on their way into our index, and we can stem all of the words in our queries to say, hey, I'm going to reduce this word to its root stem. On the other hand, that doesn't always work, right? So stemming is this powerful tool that does it just based on the surface level features of the text. I'm going to chop off the endings of some words to make them more usable, more searchable. The lemma, on the other hand, is the base linguistic form of a word. So this is how we get different verb conjugations to map to the same thing. This is hard because think about am, are, is. Those are all technically forms of the word be. To be, right? He is. They are. I am. He be. No, he is. But to be. Being. And different ways of referring to these things, right? And then a more simple case is saw versus see. They both are about vision, right? But we need to figure out how to collapse them. So a lemmatization process will create that. So to make stemmers, it's sort of an easy text cleaning process. You don't have to know this. This is like context-free grammar notation. This set of linguistic rules for reducing the terms to common letters, right? So stemming algorithms will go through this process of looking for particular endings and changing them to simpler endings, right? So it'll look for the letters IES in ponies and turn it into I. But it also might look for a Y and turn that into an I at the end of a word, right? So we will touch on stemming. We will use it. It will be nice to use, but we're not going to implement it ourselves. There are a variety of stemming algorithms that exist. We're not going to reinvent the wheel. I actually even have a found Porter stemmer that we will use in some of the assignments. So look forward to that. But let's just look at the process again. Such an analysis can reveal features that are not easily visible. So each of these different stemmers might choose to do this a little different way. The Porter stemmer ends up with sort of, it leaves a lot of I's and it cuts off all the E's, versus the Lovin stemmer, well, it doesn't even keep the I's. It still lops off the E's. And then the Peich stemmer, which is quite similar. It reduces them even more. So the idea here is not that these are all very important things to know the difference between. It's more that there's a few different ways you could say, ooh, I'm going to cut off the suffixes that are redundant across different words. Each of these has a little bit different accuracy, and some of them, every decision you make about which kind of additional process you introduce, it's going to change your search system's ability, right? So if you implement a stemmer, you might end up with a few more small errors, but you'll get a lot more accuracy and efficiency, honestly, because now you're folding your dictionary of terms, your vocabulary is going to be a lot smaller if you use a stemmer or Porter, or stemmer or a lemmatizer. So, but here's another example of how to consider this stuff. So, operating system. That's a specific idea, right? operational system. Well, that's not quite the same. If I say operating system, you know I'm talking about computers and the primary software that they run. Operational system, we probably wouldn't want that to collapse to the same thing, but oops, we stemmed. So now oper and system are our terms. All of our searches for operating system are going to pull up operational system text. Now, really think about that. That's problematic because we know that operating system is a key idea. It's a specific kind of thing in the world. This is just another discussion of phrasing, right? Phrases. But if I have collapsed collapsed both the query and all the text into these stems, these things become interchangeable. This is the drawback, right? This is also why we have redundancy. We can have a stemmed index and a non-stemmed index. We don't want to do all of these things every single time, but we can if we want to. So, stemming. It helps you create equivalence classes that are useful. It helps reduce your vocabulary quite a bit. And the basic idea is that we probably want some of these terms, some of these different forms of words to turn up in each other's searches, right? But it can reduce the precision, right? So if I type something that gets stemmed in a way that I didn't expect it to, I'm going to be kind of frustrated when the search results come back with a bunch of stuff that I don't think is related, right? So, yeah, the importance of certain words can be reduced if we allow that. So, what we've been talking about is how we end up tokenizing our text into useful bits and pieces, right? Into terms, perhaps into stemmed terms, all that. So we always have a lot of decisions to make about what we consider to be the same tokens versus distinct tokens, right? Which things do we want to collapse together? What equivalence classes do we want to make? So, and that's from, what's the balance between handling minor edge cases at one far end to making sure that critical information actually gets through at the other. There's a sort of a tension there. We don't want to, handle a bunch of minor edge cases that make it so that the critical information is lost, at least for our system, right? Maybe some systems it's critical to think about the minor edge cases of like, oh, well, this word should technically be like this because it's a very precise information set you're working with. So there's a lot of considerations. When you think about the whole process of tokenizing a document, we got to think about, what do we consider useful punctuation, useful capitalization, hyphens and spaces, the diacritics and accents that we talked about. So there's lexical considerations. And there's also the idea of, how similar words can have these similar meanings that we need to consider, right? So it's not just about the text, but it's about the idea that sometimes we need to collapse things into equivalence classes. So we'll leave tokenizing at that for now, but the big idea is that depending on what you're actually doing, what documents you're actually working with, you're going to want to include some different considerations from what we've talked about. So maybe if your band name car slang search system is really needs to keep track of umlauts for Motorhead, yeah, you'd probably need to distinguish Motorhead from Motorhead, right? But the baseline is that even if we just do the basics, which is most of what we'll do, delete punctuation, force lowercase, split on white space, that's going to cause you to miss some things, sure, just using these sort of very default equivalence classes in our vocab. But it carries you quite a long way. And the tidbit here is that you can always try. You can always try implementing stemming. You can always try implementing an additional index that doesn't remove any capitalization, right? You don't want to rely on a million billion indexes that are all doing slightly, very subtly different things, but when it's important, you can. You can make a second index that says, "Ooh, wait, here's a bunch of things that the primary index missed. Let's figure out how to consider these in the search results." Okay, so that takes us through our discussion of some of the ins and outs of normalizing text. Some of the ways that we can do that in an important manner. Now let's talk about phrase queries. Okay, so your search system, it can take a bunch of words, right? I type a few words into the search bar and it goes through, right? But sometimes I need a specific phrase, not just a loose association of all the terms in sort of a grab bag, right? You need something more than just the term index, the simple term index, right? What if I want to search for Bohemian Rhapsody, right? Now, those are a little bit, those words are not terribly common, but I promise you, Bohemian and Rhapsody, those are both sort of classical words. You're going to get a lot of classical information if there's no way, like classical music, I mean, if there's no way for your system to say, wait, they put those in quotes. Those need to go together. We're not just looking for Bohemian somewhere and Rhapsody somewhere in the document. They need to be right next to each other. This is a phrase. Okay. So how do we handle this? There's a few options. You could just say, okay, run a normal search, run the normal term search on all the non-quoted words, and then run a k-gram search on the quoted words. Break the quoted words up into k-grams and run those through the index, through the k-gram index. That would actually achieve it, but that's strictly character order based, and that sometimes has been an issue, and also that can't take advantage of our vocabulary tools we've just been looking at, right? Like, there's no stemming possible in a k-gram exact order search, right? So the idea is we want words that are near each other, but we want to do some of the nice things we've been able to do with creating equivalence classes. We want to still treat them as terms, not just break them into exact k-gram search. So, two different solutions. There's phrase indexing and positional indexing. So before, we looked at a lot of cases where it would be useful to keep track of very specific phrases, right? As opposed to just the singular terms themselves, right? United States of America, database or operating system, right? These are important words, right? So how do we index this? Well, you can create a phrase index. You can say, okay, I'm going to do it all normal. I'm going to do it all as we have done in the past. But on the side, after I've turned these words into tokens, I can build out the phrase index to be small lists of tokens, right? So United States of America. Okay, great. So that happened. That's postings of that set of tokens is in document 1. Whereas in the term index, we would see United States of America demonstrated the blah, 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 right? So that's the basic idea of a phrase index, to maintain the idea that these are still terms, right? So I could stem all of these, I could normalize all of these and still keep the phrase. Or I could decide not to, right? Maybe the capitalization is part of the phrase, right? So this is okay. This allows you to keep track of the phrases that we know are important. It's very precise too. That set of phrases being the index, being the key into our index to figure out where the postings are, is great. But they can get really long really fast, and we need to know what the phrases are that are important up front. That kind of sucks. So I mean that really sucks. So trying to come in and say, okay, I will store all of the countries. Okay, that makes sense. But oh wait, now I need to store all the cities. Okay. So as you try to do all this, you end up with a lot of effort being put into building this very key specific phrase index, and it's not flexible. You can't. The user can't put in a phrase that is not known. It just will never match. So your system, again, this is extremely precise. It will always help your system find exact known phrases very quickly. But again, it's hyper specific. So let's try to get a little bit more general. How else could we keep track of phrased words rather? Well, a nice approach, by word indexing. Aha. Okay, so maybe on top of keeping track of where individual terms live, we'll just keep track of where all pairs of adjacent terms live. By the time that we've tokenized a document, they're still in document order. So every pair of documents becomes an indexable key, right? An indexable term. So this is great because it's not very large. It doesn't add any size. It's going to be roughly the same size as the original index. A little bit longer, or no, a little bit shorter, because the last pair of words won't have another pair after it. But this lets you make sure all of the individual pairs of words occur in the document in that order, mostly. So to be or not to be, whether it is nobler, etc. To be or not to. This should sound familiar to K-grams, right? Where we're running over the text and saying, pull out this set of adjacent things, pull out this set of adjacent things, etc. So this is useful. This is good. This allows us a little bit of flexibility here. Let's see it in action. Okay, so query United States of America. Great. Okay, so we have this spread out across the document. This is a single document, we'll say, right? United by their rules, document state of all the countries in South America. Okay, this document is not about the United States of America. That's not about us this time. Jeez. Okay, so our normal term index is going to pull this up, right? Because all of the words are appearing in the document. Hooray! Except no, we don't want that, right? So a byword index is going to fail every one of these. No pair of these words is next to each other. United and states are not next to each other. States and of are not next to each other. Of and America are not next to each other. So that's good. Now let's look. Uh-oh. Here's a different document. And United states that the common, various states of decay, said this of America. This document should still not match. Unfortunately, this will match on both because in this odd case, we've got each pair of words is occurring next to each other in sequence. United and states, yep. States of, yep. Of America, yep. Oops. But this is not a terribly common mistake, right? This is going to be quite rare. It's hard to get this match when you don't actually want it. But this is the drawback of doing 2 words at a time. We could do 3 words at a time if we want. We could do 4 words, 5 words. Gets to be quite a lot, but it could do it. It could work. You don't want to go too far because it could very much explode the size of your indexing. But these are good. These byword indexes can help, track not just individual one-off word occurrences, but a little bit about their location and adjacency to each other. So, and a great thing about these is that it works on any phrase that you hand to it. It doesn't have to be a known phrase. It doesn't have to. We don't have to know all the states of the union, all the countries in the world, all the capitals of all the places. We don't have to keep track of that in a specialized index. We can just say, hey, I'm also going to create a byword index, but it can produce a lot of false alarms. United States of America, that's pretty specific because there's enough words in that order. But you could get a lot of errors with just 3 normal words that you want to occur in exact sequence. So, more on general phrase indexing, so to cover what we've talked about. So, we want queries that span more than one token. That's the goal here, right? So known specific phrase indexes are good, and they're very precise, but they take a lot of manual effort, a lot of curating to figure out, these are unique key ideas that need to be kept track of. Okay. To expand out a little bit, we can also make byword indexes that allow a more general approach for matching exact phrases, but they have some issues, some small issues. You don't want to have too many of these. And the issue with both of them is that they're going to explode in terms of their size. So think about byword indexing. The word to, right? You're going to have to create a vocabulary entry, a dictionary entry in your byword index for every word that could come after to. So to and the, to and a, to and be, right? Be as in the verb. That's a big index. It's basically the size of the language squared. That's a big old index. That's not what we typically want. So, both of these work for handling phrase indexing, but they're both costly and they're going to blow up. So, how do we solve this a different way? What else could we do to fix this? Enter positional indexing. This is useful because this gets us into the idea that the way that we actually produce an index can help us track more carefully more information about each term. Ooh, that's interesting. That's exciting. So instead of building this byword indexing where we're messing around with the terms, we can build an index that for every document occurrence, we keep track of where in the document that word, that term occurred. Now, yes, we are messing with the default indexing process. That can be a little scary, and it's also storing a lot of extra information. But this is powerful, and it brings us a lot of flexibility later on. So, knowing where a term occurs in a document is great. So we can ask a lot of questions about our phrases. So I can ask, hey, is this term right next to this other term? Because I know the position of each term in a particular document, I can say, so for this document, yes, these two words do occur next to each other. One's in position 7, one's in position 8. Just like in a byword index, which is great. But this also lets us look at whether or not a whole bunch of words are in sequence. Are they in positions 7, 8, 9, 10, and 11? We can say yes or no, right? And then some even more interesting things, and most search engines don't implement this, but in legal text you get this a lot. We'll talk about Westlaw at some point. It's a nice search system, one of the primordial search systems. So is something within X positions of another word? Is the word United States within 10 words of the words South America or whatever, right? Or are they exactly X positions apart? Or does one word come before another word? Okay, so these are all cool. This is the idea. By adding one new kind of information to our postings lists, we enable a whole bunch of new classes of search precision to our user. So let's look at one. Let's look at this situation. Here's to be or not to be. That is the question. These are our two documents. Each document, by default, when we tokenize it, it turns into a set of positions, right? To be or not to be. Those are the tokens in Doc 1. And we see where those positions occur. So let's look at our index. We're going to do the sorted version. B is the first word. Where does it occur? Well, B occurs in document 1, and it occurs in two places. Position 2 and position 6. Great. So now the postings for B are, or the one posting for B, the document ID 1, is appended with a list of the positions where B actually occurs. So now we're getting into multiple lists of lists of lists, but this is the key idea. So B, document ID 1, where does it occur? Positions 2 and 6. Great. Is, document 2, happens in position 2. Not, document 1, position 4, and so on. I believe it's clear at this point. So let's look at this. So if I now say, here's the query, not to be, and this is a phrase query. It's in quotes. So the question is, how do we break this up? We're going to search for documents first that have not to be, right? The terms themselves. And then we're going to ask for each of those documents, is not one position before 2, and is not 2 positions before B. Not to be, right? So for doc 1, we see that not is in position 4. Okay, good. Position 4. We see, where's 2? Is 2 in document 1? Yes, it is. So 2, those are in positions 1 and 5. Okay. And then B, those are in positions 2 and 6. So not is at 4. Is there a 2 at 5? Yes, correct. Great. Not is still at 4. Is there a B at position 6? Yes, there is. Document 1 succeeds on this search. So we've seen now, using this positional indexing tool, this method of indexing, we now have the ability to do generalized phrase searching with just straight up any phrase can now be searched very precisely. And again, we have added a lot of information to our index, but this information is very flexible and reusable and powerful. So this is worth considering when you build a searchable index. So positional indexing, it gives you great control and new functionality for search altogether. Allows to query all kinds of interesting stuff. So anything within 3 words of X and Y, or these 2 words are exactly 2 words apart, or these 2 words are next to each other, or this is a string of words that are all in the same, all in a row. But this increases the size of our postings. It is a trade-off. If we want these special magical powers for our search system, we pay by giving the system more space to keep track of information. It also makes the intersection algorithm a bit more inefficient. So instead of just scaling with, again, the number of documents will drive a normal term index search, right? So let's say any given term occurs in 10% of all documents. Well, if I have 10 trillion documents, it's still 10% of 10 trillion. But now, on top of that, it's the intersection algorithm now has to keep track of and run all these additional searches on the number of occurrences in each document as well. So now both the document amount and the size of each document is going to determine how our system scales. So this makes our trying to scale up to Google model a little bit worse, but it's far more powerful. So again, a potential decision to make. You might want to do this because it might be worth your effort. Okay, so what are we to do? What do we want to actually do? What's the practical advice if we're going to go through all this effort to enable phrase searching in our system, right? The common approach and the quite useful approach is the following. You build both a phrase index and a positional index. Now, that sounds quite effortful, but it's useful because a phrase index is kind of lightweight first cursory check. Like, oh, they sent me a phrase. Is this a common phrase that we all know? Is this something that we're using quite a lot? I'll go check out the phrase index. Okay, even if the phrase index is small, this might still be worth the effort. So you build the phrase index specifically, and you say, here are the key phrases. Is this in it? If it's not, then we fall back to the positional index. So, this short circuits the issues of like having to take longer to process queries in the positional index, and it helps us keep our searches short when we already know what's going on with a particular phrase. So, and again, this rests on the idea that, remember a key element here is that even though I was just described, oh my god, a positional index is so much larger, it's so much slower to build and to process, and that's fine because building the index is something that we do once. Right? So we build a set of indexes, a bunch of different possible indexes, and then we're only going to use them if we need them. So if I need the positional index, even though it's slower to run a query through, I can still do it, right? It's there, it's available. I built the tool. We'll go there when we need to, but it's there. And ultimately, we need this kind of thing because if I type the who, I'm going to need to keep track of the who, right? That's never going to work in a particular search without some kind of phrase solution implemented. So, phrase and positional indexing. We often need to search more than just our initial terms, right? Just the regular individual terms. So phrase indexes will help us keep track of common information, words that we are used to seeing quite often. And positional indexes open up the doors to all kinds of other processing power but also, cover, at least at the minimum case, hey, are these words all next to each other? I don't know these phrases. They failed my phrase search, so now let's do a positional search. Great. So we've added more indexes. Oh, great. Oh my gosh. But it's useful. It's very powerful. So we'll eventually check out the Westlaw legal search system that makes great use of this positional searching. In fact, the way you write your queries as a user, you can specify things like this word is exactly 3 words apart from this word, that kind of thing. So high-level recap. We've discussed how to define a little bit more our vocabulary. So specifically, what kinds of equivalence classes are we going to make? What do we want to be the same? What do we want to be different in our vocabulary? Those are questions that one must answer when building their search system. Also, how do we process longer chains of queries, right? So phrase queries. And we've also introduced this sort of big idea, the positional index, a very powerful tool for getting really persnickety with our searching. You know, we can enable the user to do some of this stuff, or we can use it for other intermittent processes that we want to use. But it costs something. It costs space the first time we build the system. So, final thought. What are some types of documents you might want to search for where the exact order of terms is absolutely critical? All right, thanks. Take care.